chapters 8, 10, 12, and everything about drugs that we learned in the lab. There's like 7 drugs and the mechanisms that we learned through the video. And again, I put some of those PowerPoints on serotonin, LSD. They're actually on the handout of 8, or the PowerPoint of 8, that you can go back and see. 13 is not on it. If you look at your study questions, I don't know, the last 5 or 6 involve chapter 13, because sometimes I used to cover it, but it's not going to be on the test. So you can come and see if you're not sure about those. But that's the test. What we have to do for this week is we're going to finish chapter 10 today and hopefully begin chapter 12. Chapter 12 will be an abbreviated type of chapter where I've taken a lot of the material and summarized it into like the 7 steps of muscle contraction relaxation, which actually takes into a lot into a small amount. So it's not as bad as it's not as detailed as some of these other chapters. So we'll finish up 10, start on 12. On Wednesday, we'll finish up 12, and then have the class, and any time after that people want to say to review, to look over those, I'm already chalked out, to look over those extra questions. Again, those extra questions that are online are critical for understanding what kind of questions you're going to see on the test. The study guide questions are just very general questions as far as do you know the basis of things. But actually being able to put things, integrate them together, and to critically think, like the questions will be. I'm giving you examples of those types of questions that I recommend by Wednesday you have looked at those, try to answer them, and then we will try to, make sure that you understand them before it ends. So there's no lab on Wednesday, and there's no lab on next Monday. So tonight's lab, for the people that haven't had it, is on EMG. Which will be the last lab for the lab test, which will be in a couple of weeks. But so there's no lab Wednesday or next Monday. Wednesday will be, review session for anybody that wants to stay. I'll talk as long as people want on that day, and then Monday is obviously the test, in which you have till 8 o'clock or something if you need it to actually complete it. So where exactly did we leave off? Did we actually mention smell and taste? Did we do pain? Pain. Did we do referred pain? Okay. All right. Got it. So we sort of left on that because that was pretty important. So, we're going to fill this chart in, finish up. You're going to see 2 of those sentences are like one line. 2 PowerPoints or something. So that won't be big. Again, this is big. You do want to, like we did in class, you do want to understand the gate theory of pain in detail. You want to be able to draw these and explain what's happening at each step. What's happening with no pain, what's happening when pain signal actually happens, and you have strong pain, and how something sort of, whether it's acupuncture or some sort of rubbing, some sort of non-painful stimulus can modulate the feeling of pain. Okay, it's sort of a small neural network we have here that actually shows it. And so, are there any questions about that?
So the theory is all 3?
Yeah.
Just the modulation?
Yeah, I mean the theory is involved on I don't know specifically how it's going to be. I mean the gate part of the gate theory is this, but you sort of have to understand sort of the normal mechanism of pain transmission to really kind of get it. So practice doing that. Okay. Practice before next Monday, because you will definitely need to know it next Monday. And I guess we'll fill that in a second. So we have all that. So referred pain. We sort of have an idea of referred pain. What most of us are familiar with, if you have a heart attack, that you'll feel pain on your left shoulder and arm. There's also some other ones here that are sort of interesting that maybe we don't hear about as much. Gallbladder or liver, it might be your right shoulder. And you're not memorizing all these different ones. What I want you to understand is why. And we're going to see a term again today called convergence. Again, overall convergence, or what we're going to have for the nervous system, is when we have more than one neuron that converge on a secondary neuron. Okay, we saw that for some of the areas less sensitive in our body, like the back of our arm. We had convergence of touch receptors, so you couldn't distinguish 2 points. this is something like that. And so referred pain basically is if you look at some areas of the spinal cord, we find that we're going to have these primary sensory neurons from the skin, basically converging with other pain receptors which are located on some of our internal organs. And so both of these are innervating the same secondary pain fiber, which means in general that if there's pain to either of these, the brain's going to receive one signal, and it's basically has to make a decision whether this pain signal is coming from the skin or from that internal organ. And you can kind of see the words here. Since most of the time we're being exposed to painful stimuli, via the skin, because these are nice and well protected, the brain sort of assumes, and don't ask me beyond that, all the processing, but basically assumes the pain is coming from the area of the skin, and that's referred pain. That's why you feel that pain. It's literally, it's not, again, something just in your head or anything like that. Well, it is, your brain, but it's basically based upon, a real physical manifestation area in which you have convergence of pain receptors from the skin with those internal organs, so the brain doesn't know which. Whether it's the left shoulder and the heart, or this is somewhere else for the kidney, which doesn't make me happy. I don't really want to see that. But any questions about that? That's referred pain, convergence. Olfaction, smell. Again, we already said last time that you have to realize that all the senses, except for olfactory, is going to go to the thalamus and then the cortex. This is a very old sense. And bottom line is to start to fill this table in. So the two features that we're trying to sort of give us a table and distinguish all of these senses are the type of receptor it is, the sense, is the receptor itself sort of one unit, in which the dendrites, which are actually then the receptor, is part of the sensory nerve, or is it a specialized cell that will synapse upon the sensory neuron? All right, that's the first classification. The second classification is the stimulus type that it responds to. And again, there were like four. There were chemoreceptors, mechano, turbo, and photo. So in most cases, they're one of those, except for, of course, pain. So touch, somatosensory touch, was dendrites or specialized cells?
Dendrites.
Dendrites. Even if they're wrapped, they're still the dendrites. And touch is mechanical. Pain, dendrites or specialized cell. They're actually the free nerve endings, so they're dendrites. And what do the pain receptors respond to? I hear a murmur. Chemo, mechano, turbo. So they're the only one that really responds to more than one type of stimuli, because it can all cause pain, and we care about that. Okay, olfactory. It might not be obvious from this, because it's sort of not very detailed, but basically these are the dendrites that are going to basically recognize the molecules and send it, this is the sensory nerve to the olfactory bulb, and then of course to the cortex. Therefore, olfaction are the dendrites as well. And what is smell? What are we responding to over there? What are those receptors responding to? Chemo. These are odorants. These are chemicals that they're responding to. That's all you need to know about olfaction. I'm not going to go into detail of that. Just realize, of course, that it goes to the olfactory bulb and then the cortex, and that they're dendrites, and it's a chemoreceptor. We've got all this here. It's cool. But, anatomy. Woo, anatomy. Taste or gestation. Almost just filling that chart as well. It's got a lot of information here. There's the tongue. So, specialized cell or dendrites?
Dendrites. Specialized cell.
So the taste buds are a specialized cell, which finally we have another one, which will synapse upon the sensory neuron. That was the other type. We don't have one unit here. We actually have a cell that's going to transduce the information, okay, the taste ligand, into neurotransmitter, so it's electrochemical now. But it's not one unit. So here's our first example with taste buds of actually gestation or taste being a specialized cell, taste bud. And what is it? Taste ligands, chemo. Okay, that's what it's responding to. If you look at all this, everyone's got basically some different channel that's involved, depolarizing. We're using calcium. Yeah, we don't have to memorize that. Okay, you don't have to memorize what bitter does and what sour does. But they're all, going back a second, they're all going to cause some sort of depolarization, which is going to cause neurotransmitter release on the sensory neuron. And of course, whenever we're releasing neurotransmitter, who comes to be the big player? Calcium. So we talked about at the end of the neuron, nerve terminal, voltage-gated calcium channels cause neurotransmitter release. Same thing on when we're talking even on a specialized cell, a taste bud. Whenever, and we'll see another one today, anytime we're releasing neurotransmitter, it basically is calcium mediated. We're going to have calcium channels. Calcium's going to do its thing in here to cause release of the neurotransmitter.
So the calcium comes after the release of the neurotransmitter?
No, the calcium is before. The calcium mediates, we basically have a depolarization that opens up the voltage-gated calcium. Calcium comes in and causes the exocytosis of the neurotransmitter, here and in the nerve. That's the end of taste. So those two senses are just like filling in the chart. Because we spent a lot of time on touch, pain, and we're going to spend a little more time on hearing and sight than we just did.
Is calcium mediated with just gestation, or is it all the time for neurotransmitter?
Yeah, anytime we're releasing neurotransmitter, at least that I know of, in every system, we're using calcium. We'll see it again in the eye as well. So hearing. Okay, this time, the signal that we're going to be basically transducing or changing is actually sound. Sound are pressure waves. And we're going to show you that the ear is an extremely complicated organ, and we're going to go through a lot of different transformations. We're only going to concentrate on the last one. But when we're talking about sound, we have to sort of kind of get these two ideas, and there'll be sort of a better picture of it coming up. But when we're talking about the strength of the signal, that's how loud it is. That's going to be basically indicated by the amplitude of the sound wave. All right? If you look at the sound wave, okay, this is not millivolts like we've been looking at for these graphs. This is sound, so this is decibels. And so a louder sound means a stronger amplitude, okay, a higher amplitude here. So that's what, when we're talking about the strength of sound, we're talking about, I should put that on the same thing, the amplitude. That's how loud it is, okay? And the higher those are, that's the bigger the pressure wave, the louder it is. Another thing we're going to have to deal with when we're talking about the transduction of sound is we also have pitch. We have low pitch, very low pitch, very high pitch. Okay? We have to be able to decode that. The brain has to know what's low pitch and what's high pitch. When we're talking pitch, this is why we're talking the frequency of the sound wave, not the frequency of action potential. So the frequency basically, or how close these are together. Okay, just like we did for action potentials, but these are sound waves. And so you have basically ones that are further apart and ones that are closer together. This represents higher frequency, higher pitch, higher pitch. Okay? So here we're talking about, again, you just want to distinguish that you don't want to, these are not action potentials. We'll look at frequency of action potentials again, but here we're just talking about sound waves.
So if they're further apart, it's a deeper pitch?
It's a lower pitch, right. So this would be a lower pitch than this, okay, because they're further apart. But we're looking at decibels now. We're not looking at millivolts. So kind of have to know that. Again, all this is saying what I just said. The ear is going to transduce all this and be able to figure out what it was. We're not anatomy. We're not memorizing all this. And really, you're going to see in a minute, we're going to just concentrate within the cochlea as far as what we really need to know. But you want to step back a minute and look at this marvelous little piece of machinery here. And we're going to kind of go through a few steps of this just for fun. But overall, we're going to be basically doing a lot of transductions here. We're taking these air waves, these pressure waves, which are in the air, we're going to basically change them into vibrational waves and then fluid waves before we get to the electrochemical. So we've got several transformations that are going to happen. And this sort of, from the book, and this describes each one. Don't memorize this, okay? I mean, you can know it, but we're going to follow it. Okay, I'm going to tell you when, like, hey, let's get ready for the test. This is simply going through, looking at sort of the step-by-step of what's going to happen. But we're just going to concentrate in a minute on this, the actual hair cells in the inner ear and how they're changing those signals into electrochemical. But it's pretty cool. So we have this idea, as I started to say, we have these pressure waves. They're going to hit the eardrum and be converted to vibrational waves. And again, I don't really care for following what they're saying. But in the middle ear, the vibrational waves are going to continue and be amplified by these bones. And of course, that's connected to the inner ear, which is fluid filled. So we're going, again, from air waves to vibrational waves, and now we're going to have fluid waves. Okay? Again, it's just saying this through the oval window. Now, what we're going to basically talk about in detail will be this. You know, it's not, you can't see it through here, it looks like a little cartoon, but these fluid waves are going to press down upon the receptors that are going to change the signal into electrochemical, the hair cells. And so that's going to be the point of impact that's going to be changing into electrochemical. And so we're going to look at just this in detail. But again, it's nice to see this whole process of air waves to vibrational waves to fluid waves, and finally a mechanical pushing to be electrochemical. You know, and then of course the idea of we're going to flow back out. You know, I mean, you know, you have a wave here that's going through it, so it's going to basically go to the other window to finish it up. But there's sort of the transduction. Again, just to see it. Don't try to memorize those steps, but it's sort of cool to see the whole thing. So here's where we start looking at. We're going to take the inner ear, the cochlea, and we're going to unwrap it a bit so we can examine it. And, you know, again, don't memorize all this right now. We'll kind of look at this. But the idea is we do have 3 fluid-filled compartments. Okay, kind of see what they are. We're really going to be talking about the middle one, the cochlear duct, and specifically this, okay, the organ of Corti. We're going to blow this up and look at what happens. So, a lot of words not to memorize for this class at least. Now, let's examine where the action is going to happen here. We take a cross-section, and here is what we're going to concentrate on, and we're going to make it sort of bigger than the next one. The organ of Corti, we actually could see sort of, you know, again, the cochlear duct, these are all fluid-filled, but the idea is here are going to be these hair cells that are basically innervating or synapsing upon the nerves that are going to be the cochlear nerve. And that's the organ of Corti, and there we go. Let's look at that, and we're going to show you what happens. So this part you have to sort of understand, and what we're looking at, we have hair cells that synapse upon the sensory nerve, that all these axons will form the cochlear nerve. We have 2 membranes that are important. Okay? The tectorial membrane is above it. The fluid is going to push down upon that membrane to bend these hair cells. And below it is the basilar membrane. And that's going to be important in a minute to talk about how this frequency of sound is coded, this low and high pitch. So these 2 membranes are important. But here's the structure we're going to show you how it works. This is the only thing we have to know, really, for those last couple of minutes. What this looks like and then how it's going to work. The overall, and then we'll do ABC, and if you've got the handout, you sort of see there was a figure in one place, that helps. But overall, this is the idea, we're gonna have fluid waves that came in from the oval window, push down the tectorial membrane, bend these hair cells, and then that's gonna transmit the message, message on. So it's a mechanical force. So there's A, B, and C, A, B, C, and then we have it all together. So you should have this figure all together. So let's kind of go back. So this is what we're concentrating on, the actual transduction, the actual changing of all this, which initially was sound, to electrochemical. Kind of that's what we're focusing on in this section of the course. So here's what we gotta know. That at rest, which means no sound, the stereocilium, the hairs of the hair cells, this thing is basically straight up. But, even under those conditions, the cell is partially depolarized, which means it's releasing a tonic level of neurotransmitter onto the sensory neuron, sending tonic levels of action potentials to the auditory cortex. That's at rest. So partially depolarized and sending some signals. Yeah, tonic signals. Okay, as far as sound goes, there's sort of going to be two phases, because this is, an actual action. This is a fluid wave, and as fluid waves go, if you're in fluid and something pushes you this way, you're going to tend to flow back the other way. So here we go. The idea of excitation is when we finally make it to the fluid here, and the tectorial membrane hits down, it's going to bend the hair cells in a particular direction. It's going to bend it toward the largest of these stereocilia, and that's called the kinocilia. Okay, written here. As that happens, that's going to further depolarize the cell, causing more neurotransmitter release, and therefore more action potentials. So you had a tonic level, now you have an increased excitation, but again, in the wake of that fluid wave, oops, I went the wrong way. In the wake of that fluid wave, we're actually going the opposite direction, away from the kinocilium. And so now the cell is actually hyperpolarized compared to rest. So it's actually now going to release less neurotransmitter. Now let's look at it again all together. So take a drink. So it's a little different than you might think in the sense that, with no sound, we're sending some signal to the brain. And so again, with no sound, when these stereocilium are straight up, cells partially depolarized, causing some neurotransmitter release, tonic level, action potentials to the auditory cortex. When we have the sound reach it there, and we have this fluid wave pushed down, we're going to have basically a period of excitation, okay, bending toward the kinocilium, more neurotransmitter, more action potentials, followed by a brief inhibitory phase in which now we've extended the opposite way, away from the kinocilium, hyperpolarized, and so there are less action potentials than there were with no sound. And then, of course, you go back to normal. So you sort of have this region of of having an increase in action potential and then a great decrease before you have, again, this tonic level. And the brain can interpret that as sound. Okay?
So is the big part in there the kinocilium, or is the action called the kinocilium?
The biggest, let me go back to that picture. Well, the wrong way. The biggest of the stereocilium, there are different sizes, called the kinocilium.
Okay.
Okay? And things are bends toward that one at the beginning and then away from. When it's bending toward that larger one kinocilium, that's when it's more depolarized and more action potentials.
So the depolarization doesn't happen at rest, right?
Yeah, there is. It's partially depolarized.
Partially?
Partially depolarized, causing some neurotransmitter release at a tonic level. It's just that it increases and then decreases during this period of hair cell activation.
So it increases during excitation?
But I mean, as soon as you excite it, yeah, it's going to, because it's a fluid wave, it's going to actually bend the opposite way and have a small period of hyperpolarization, less than even was before. And then things stand back up. because again, it's sort of a physical thing with, you know, something actually moving through fluid. You push it down, it naturally goes sort of back. And so again, but the brain knows this is, you know, it understands again how to decode this, that this represents a sound, basically. Now why? Well, I'm not sure. I like to think of it as if you're trying to be very sensitive to something. Let's say you're in a car and you want to be able to hit speed right away. It's nice to have the car started versus having to start the car from nothing and then sort of react. That might not be the actual reason why, but this is what actually happens. So you've got to realize, again, that tonic level followed by activation, you know, increasing depolarization, and sort of hyperpolarization before it goes back. So already we could fill this in before we add a couple little details here. Hearing, dendrites or specialized cells. And what type of receptor? Mechanical. It's a physical pressure pushing down on those hair cells. Now, just like we did with every other stimulus for sensory receptors, when we're talking about the strength, okay, of the stimulus and how long it is, it simply had to do with the frequency of action potentials. Okay? So just like for any of the senses, if we were going to have a stronger signal, we had a higher frequency of action potentials. It was closer together. The same thing here. If it's a louder sound, these are going to be, we're going to be bending it further. That's going to basically, you know, cause more depolarization. We're going to have a higher frequency. These are going to be even closer together. If it's a longer sound, this will be extended for a longer period of time. This isn't different than any of the other senses, right? This is exactly what we said, that the stimulus strength was going to be related to the frequency of action potentials. Same thing. But the one difference that we've got to deal with is the frequency of sound. This is why it's like frequency. Remember, the frequency of sound represents pitch. How is the brain going to know it's low pitch versus high pitch? Because of this. So, if you look at the basilar membrane, kind of shown here, as it says here, it has different degree of thickness. Okay, this represents near the oval window, because remember we unwound the cochlea here, and on this again are our hair cells, and my hair cells are beautiful, and of course they are connecting to the axons that will form the cochlear nerve, which of course goes to the thalamus, and then to the whole board here, auditory cortex. And it just so happens, just like we said with somatosensory, etc., you know, on the visual, that within the cortical region, there's sort of a map that's similar to it. And so it sort of has this frequency map, okay, this pitch map as well. So the way it's going to work is, because of the stiffness of it varying here, that high frequency sounds, so we'll just put high pitched sounds, that have been transduced into this fluid wave, only bends the hair cells nearest the oval window. Okay? They have enough energy, this is stiff, I guess they're harder to bend, so high pitch has enough energy to bend those, and once that takes the energy, well, it's not going to bend any of the others. So a high-pitched sound will activate cells near the oval window, and the brain, of course, will know from that axon that this represents the high frequency, high pitch.
Are those the hairs in your ear?
Those are the hairs in the inner ear. Those are the stereocilium that we just saw up there. I mean, we didn't see it on there, right? That's the inner ear, right? So those are those guys that are sitting on.
Okay.
Yeah, so we're all we're looking at again is what's happening here, but now on the basilar membrane, that the hair cells which are located nearest the oval window, okay, they're going to respond to high pitch, okay? So very high pitch will bend these, they won't bend any of the other ones further away. And that will then transmit messages to that area of the cortex, and of course our brain deciphers that's high pitch. If you basically have a lower pitch, okay, and we're setting it, it's not going to have enough energy, fluid energy, to bend these. But remember, because this is different stiffnesses here, there'll be enough to bend some of these closer in the middle here. And therefore, this mid pitch might be somewhere again on the corresponding auditory cortex. If you go to low pitch, very low pitch, okay, it's not going to bend any of these. It's going to bend ones the furthest away from the oval window. And that's how the brain's going to recognize low pitch. So again, just go back to that picture. I guess we can go to this. The key with this is, it is going to be what determines pitch, what determines how the brain's going to decipher whether it's low or high, is basically which hair cells it's going to activate. So ones which are closer, this is close, further, ones which are closer to the oval window, so at the beginning, are going to react to the higher pitch and bend. The ones that, the lower the pitch, the hair cells further away from the oval window are going to react. And again, we have a corresponding map on the brain to decipher that. So we hear from like basically 20,000 hertz to 20 hertz, it's a big range. Literally, our hair cells along there, each one's responding to a different frequency of sound. That's pretty good, actually. These things are pretty intense. Any questions about that? Yes?
So what exactly is the oval window? Just a part of what they're...
Let me kind of go back to the anatomy of it. Okay, so basically, the oval window is exactly, when we're connecting from this vibrational waves of the middle ear to the inner ear, that's where it happens. Okay, so that's the exact transition. This vibration will basically, at the oval window, that's where it's attached, will cause these fluid waves to actually happen and then bend the cells here. The other window is where sort of that residual wave action will dissipate out, it's just fluid. But where the energy is actually coming in, where we're actually changing vibrational waves to fluid waves, is at the oval window. And so the hair cells, remember, the hair cells are located all within this. The hair cells closest to the oval window here, they're going to react to higher pitch. The lower the pitch, they're not going to be able to bend these. They'll bend these in the middle here. Even the lower pitch, they're going to bend ones only over here. So the hair cells located on there, each one responds to a different pitch of energy. These the highest, lower, 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 lower.
Where's the eardrum?
Here. So the tympanic membrane is the eardrum. That's the initial changing of these pressure waves into vibrational waves.
Okay.
So tympanic membrane.
So the oval window's behind the eardrum.
Yeah, it's basically on the other side. The middle ear has the bones, which are basically taking those vibrational waves and amplifying it, and that's sort of the connection between the eardrum and the oval window and the inner ear, which is all fluid. So kind of there to there. You have another question?
Yeah, I was just wondering in terms of like hair cells, you're talking about the inner ear, so it doesn't have to do with like...
No, I know, that's fine. Yeah, no, it is, that's what they call them. It's the inner ear, it's what's happening exactly. It's not the hair that's sort of, I need to trim the hair on my ear right now. That's,
Do
no.
those hairs have anything to do with those? No.
No.
It's just, those are all outside to help keep debris out of it.
Yeah, exactly. So they just call these hair cells, those are the actual transducers in the inner ear, because again, those stereocilium look like little hairs, I guess. And they want to confuse us, I don't know. Any other questions about hearing? A little more complicated than the others, but not too bad. All right. The class is silent and all already. Okay. That's what I do. Are we ready for vision? Vision is our most complicated sense.
More complicated than...
Oh yeah, and we're only going to like bow and barely touch it. Okay, you could spend months and months talking about the sight. It's very complex. 70% of our sensory neurons are involved in sight. Because if you think about it, we're not just, I don't just need to know, like, you're over there, right? I need to know every detail. I need contrast. You're moving. I need motion. You've got to analyze a lot coming in from your visual system. So it's, like, really complex. And we're just going to be in all of it and just add a couple, just the first layer of it. Not even coming close to its complexity.
Then on the little caricature thing that depicts the activity of the senses, do you know what I mean? Like the drawing, why are the eyes so small?
What do you mean?
Like
I know which character,
this,
sure.
like this guy, right? Like the one that's like wrapping around the brain or something like that. Here, hold on. The somatosensory cortex person, like the face one.
Because that somatosensory cortex is simply recognizing whether there's pressure on your eye, right? We're not reading Braille on our eye. That's there, but where is all this visual information going? To the visual cortex, okay, and the occipital lobe, and that's where all the processing is occurring. So that's simply because we don't have a lot of touch receptors on the eye. That answers that.
Oh, so that's all touch.
That's all touch. Somatosensory is simply feelings of touch. That's sort of a good question, though. I had to like think about, what are you doing? Oh, yeah. All right, so what do we need about the eye? Again, all these are words, but we are transducing light. And when it comes down to it, again, we already know we're going to have basically the optic nerve to the thalamus to the visual cortex. We are not doing, of course, anatomy, okay, with all these lines. We're going to concentrate in a minute on the retina, which are actually containing the photoreceptors, right? We're concentrating right at the level of action here, right, the changing of the signal. And that is on the back of the eye. Of course, we're going to focus it on there. And we are going to talk about, in a couple slides, these two regions, which are going to be the area of sharpest vision, the fovea, and the optic disc, sort of the blind spot, where, again, everything's leaving here. We'll talk about that in a minute. But we're not going through all this other anatomy. But because we did this in lab, we're going to be looking at sort of this a little bit more about the pathway. And the idea of when we get to the consensual light reflex, we did the pupillary reflex and the consensual one. It has to do with the fact that signals cross, that are coming in one eye, actually instead of fully crossing to just affecting the other hemisphere like our senses do, we showed, basically there's going to be signal from one that are going to go to both hemispheres. And the same thing this. Part of the reason, again, is that vision is much more complex. We want to be able to see what? Three-dimensional, and you sort of need two inputs to actually see 3D. So, all the information comes from one eye. Part of it's crossing at the optic chiasm so that it actually goes to both hemispheres, and same the other. And that's at the optic chiasm. Okay? So you can see from a cross-section here, or whatever you want to call this. I forgot. Longitudinal, what is this thing?
Cross-section.
Okay. What is it? It is a cross-section. Yeah. Okay, I don't know. That's anatomy. I need to look at anatomy at some point. But anyway, all this is showing is that it's going to go to the thalamus. You don't need to know the particular region, and to the visual cortex. Just it matches all of our senses. Okay, let's look at this in more detail now. So we did this in lab. We're going to have to know it for the lab test a little and other detail down the road. But we need to know this for this test. And so the idea of these two reflexes were the following. That although we're talking about, again, signals going to the thalamus and the cortex, we're going to have a little diversion here, and we're going to have a reflex action. So if you shine a light in that eye, you want that pupillary constrictor muscle to constrict to protect the photoreceptors. You want a reflex here. And so, again, what happens is, if you just look at this one eye, this normal one, we have light hitting those photoreceptors. Okay, the afferent does have a name, the optic nerve. And if we look at this side here, it's going to still do thalamus, etc. But we're also now going to go to the midbrain, and we're going to send an efferent, cause constriction of the pupillary constrictor muscle, make the pupil smaller. Now the interesting one is the consensual. I guess they're both interesting. But why, when you show a light in that eye, does that constrict? It's because of the optic chiasm. So if you look at a signal here, okay, at the optic chiasm, now that signal is actually spreading to both sides. So not only are we going to have that reaction as a reflex, but because that signal spread to the side, we have concurrent, basically, pupillary constriction of the other one. You shine a light in that eye, the reflex action is they will both constrict. Again, because part of the signal is crossing to reach both sides at this optic chiasm.
And the optic chiasm is the efferent?
The optic chiasm is where, I mean, these are basically, these are the, the optic chiasm is happening, this is afferent signals. This is signals from the optic nerve up to the brain that are crossing. So we're taking, processing the information from light, through the optic nerve. It's the information at the optic nerves that are crossing on the way out. Okay,
Is there a synapse at the chiasm? Or?
There's multiple synapses at the chiasm. I mean, that's what I mean. This is like, really sort of drawn very just simplistically. So there's multiple so that we can actually then have signals then basically go both ways. So that's why both sides are going to react. But this efferent is separate, right? They both have their separate efferents. This is kind of going behind the optic chiasm. This is not part of it.
So the cranial nerve 3.
And again, you don't have to know it's for the. You don't have to know that name as far as part of this test. And there's actually a different name for the lab test that we'll use. But anyway, yeah. But you have to just understand the mechanism here. But you have to realize this optic nerve is the afferent. But yeah, it is the optic nerve that's exchanging, that's crossing, so to speak, at the optic chiasm exchanging. So it is the afferent system that are exchanging. This is that they're both going to react. So you get an accident, and somebody's going to shine a light in this eye. And let's say this constricts, and this doesn't. Let's see if we can potentially start to see where there might be some damage. So we put a light in this eye. Again, this constricted, the pupil constricted is normal, and this did. So do we think there's anything wrong with these photoreceptors?
No.
How about the optic nerve here?
No.
Probably not. How about, I guess this is the right eye, the right efferent system here?
Yes.
Or if I do right up top here. This efferent's okay. This is constricted. How about this efferent? Or somewhere in this region right here. So you begin to localize, okay, we can't really know it's exactly if it's in the midbrain or if it has to do with this cranial nerve or that connection here, but we know it's localized here, that there's some sort of, there's some sort of damage here. And of course you can put a light in that eye and start, individually and see it too. So you can get some information of potential, brain injury basically by doing that. You should have, where you shine a light in the eye, they both are going to equally constrict, okay, based upon this. So that's from the lab. That's what we need to understand for this test coming up a week from now. It's sort of this slide here, what we just discussed about these two reflexes. Any questions just about that? So when you look at the retina, this is the place where we're going to be transducing. There's actually 5 different types of neural cells. Okay, you can see them here, and they're all listed. You can see it here. Let's actually look higher. Now the key with this is, and we're going to make it simpler, that we're really only going to concentrate on 3. Because what's going to happen is, and it's sort of weird when we actually go through it, light has to pass through, under most places of the retina, all of these other neurons to hit the photoreceptors, which are going to transduce the light signal into electrochemical. Okay? Now, the things we're going to have to know will be, and if you can go to the next slide, is sort of this, and this. Those 3 out of the 5. So light's going to travel all the way through. It's going to be the photoreceptors, the rods and cones, which will change light into chemical. They synapse upon the bipolar cells. They synapse upon the ganglion cells. It's the axons of the ganglion cells that leave the eye as the optic nerve. So that's the pathway of light that we're gonna talk about. Light's going all the way through here, activating the photoreceptors, synapse on bipolar, synapse upon the ganglion. These other 2 types, horizontal and amacrine, you see they're sort of in. They are modulating some of these signals, and we're not even going to get into that, right? Like I say, there's a lot of processing that happens just within these before we even get to the brain, because we have to, again, we just think about it. We have not just sort of, a photon of light. We have to distinguish color and shape and motion and contrast and all kinds of things. So there's a ton of this processing we're not talking about. So we're simply, if you want to call it simply, going to show you how this happens. Light going through, how these photoreceptors work, and then those 3. So photoreceptors are going to synapse upon bipolar and upon then the optic, the ganglion cells. So, you saw in that past slide, we talked about convergence, and here we're going to talk about the fovea. I said the fovea was the area of sharpest vision. It's near in the center of vision, okay, where I'm looking at you right now. Who do I look at? I'll look at you right now, okay? I'm looking at you bright, trying to basically focus you onto the fovea because it's the sharpest vision. And there's sort of two reasons listed of at least why it's sharp. One of it is, unlike the rest of the retina, again, if you just sort of remember, take the back of this, and unlike the rest of the retina, in which light has to pass through all these layers of cells, okay, showing here, basically light has to pass through all these layers of cells in the periphery, and then basically activate the photoreceptors, which will send signals going back. The fovea is sort of what I call the Moses effect. There's sort of a parting here, and so now the light's able to really directly hit the photoreceptors. That seems like it's going to be a little sharper vision already, right? You have less of sort of this distortion caused by passing through these other cells. That's one reason. Okay? The other real reason has to do with this concept of convergence. If you remember, if not, we'll sort of redraw it. Okay? Again, I got to draw my guy. Okay, I know he's happy now. He's like, he's tired of me drawing him. Okay, we drew an area in the fingertips, and we drew that. And when we looked at this, we said, okay, again, that this is more discriminating, higher density of receptors. The receptive field on the sensitive region was smaller. Now, the idea of convergence on this also was the idea, again, we have large receptive fields, that if you look at less sensitive areas, not only are there less receptors, but you actually have convergence, okay, and let's say this is the secondary fiber here, the secondary nerve fiber, to the somatosensory cortex, so that not only can't you distinguish, 2 points easily, because it's not as many receptors, but basically, if you do any points on this, the brain is going to say 1 point, right? It's not very discriminating. There's a lot of convergence. Versus this, not only are there more receptors, but there's less convergence. There's a 1 to 1 to 1. You get to the cortex, it knows that these are 2 different points, okay, by touch. Look at this. It works the same way, basically. If you look at the area of the fovea, you have much more of a 1 to 1 to 1, okay? A 1 to 1 to 1. So if you look at 2 points, now we're talking 2 visual points. You want to see how much detail can I see when I'm looking at when it's hitting the fovea. You can see that 2 points of light that are this far apart should be seen probably as 2 points, on our brain, okay? 1 to 1 to 1, not very much convergence. But look in the periphery now. Okay, in the periphery, you start to see 2 1 to 1. Okay, there's some up there in which you have. Where's some other ones here? There's ones where you've got a couple of them coming to 2 to 1 again. Here's all 3 of these will end up going to 1. So any points along here, even that same distance, are going to see as 1 point. So there's less convergence. You're going to see less detail coming from the periphery. Okay, which makes sense, right? And we know that. We'll talk about the advantage of having the system here, but right now the fovea is the area of sharpest vision because it has less of this interference passing through these other neurons, and there's less convergence. There's more of a 1 to 1 to 1 ratio. What else are we looking at here? Cones and rods. The fovea also has the highest concentration of cones, and cones detect what? Color. Okay? Yeah, we'll come back to that. Rods detect black and white, and they are highly localized in the periphery, and then cones are in the center. So we'll come to the active nerve. So the idea of that is, and we'll look at this again, we all sort of know this. So rods, again, are more detecting black and white. Okay, so we have our rods sort of in the periphery more, and we have our cones detecting color in our fovea, our central region, when we looked at that. Now you don't have to know that there's basically at least 3 types of cones for these different pigments. I think there's even more now. You don't have to know that. but you do have to know that rods are more sensitive. So rods detect black and white, but they're more sensitive to light than the cones. So as little as a photon of light can activate those, where the cones, which detect color, are less sensitive. You need stronger light to actually see it, but if you see it, you'll see color. So again, if you we have this idea, cones are detecting color, rods are more in the periphery, but these are more sensitive to low levels of light. So there's 2 points I want to make with that. Again, so the fovea, cones are color, but the rods are in the periphery. If you think about, there's one thing is that you can actually, sometimes we do this in the lab, in the lab that we do, that I didn't do it this time, is you could basically have a person, close their eyes, you put something colored in their hand and have them hold their hands out and have them look forward, and they're going to slowly basically move their hands, closer to center, and you ask them, they can't cheat. They're looking forward. You ask them, okay, when can you see an object? Okay, and I could see an object here. And they're like, can you ask, can you see the color? And I can't. Okay, and then I see the color. Okay, so sort of makes sense that when you're in the periphery here, you're hitting mainly the rods, so you're able to see something in the periphery, but you're not able to determine its color. But as it gets toward the center, now you're able to distinguish color. But think about the setup here, and think about sort of survival again. That let's say we're sort of in a dark room, and that bear comes in. That bear keeps following me, and so and I'm looking at you guys trying to talk about something, and what I want to be able to see in that low light is there's a bear over there. There's some sort of motion over there. So I want something very sensitive, okay, that can detect very low levels of motion, very low levels of light. But do I need to know right at that moment that it's like a black bear?
No.
No. But what am I going to do?
Right.
Well, what am I going to do first, probably? Okay? You're going to turn and focus using now your most clarity, your fovea. So now I can see, yeah, that's a mean brown bear and I better run. Okay? So for survival and just in general, it makes sense to have the periphery where you don't need to distinguish, have as much accuracy, but you want to know something's there. And then to really assess things, you basically will always focus toward your fovea and actually get as much information as you can before you know what to do. And again, it's not just bears, but it's kind of how we're going to do it. If we really want to be figuring out something, I'm going to be looking directly at you. I'm not going to. Well, I might see like if you're on the phone, right? I'm like, I'll just see you moving here. But if I really want to know, you'll change your focus to directly on it. So you're going from the periphery toward the center. Yes.
Excluding psychological stuff, if you can't see well, that basically means your phobia is not in good order.
No, there's actually there's conditions in which there's certain pigmentosins where you actually narrow it so you lose peripheral vision and you only see that, and then there's others, and I can't remember the names of them right now. There's others, macular degeneration that you're losing from the center and then out. So there's 2 different types of main types of that kind of blindness, progressive.
So what happens when you're colorblind?
When you're colorblind, again, genetically, you have it where you don't have functional cones. You still have cones there. It's not like rods or anything, but those ones just are not functional, so you can't see red, and you just are missing the pigments. Anybody colorblind? Okay. What?
So dogs don't have cones?
Dogs can't see color?
I didn't know that.
They say that's true? Okay. I don't know. I'd have to Google that. I'm sorry. I don't know about dog vision. Let's go back 1 second, and then we'll do the actual transduction. So I said we were going to mention the blind spot as well, and sort of again the optic disc or the blind spot is where if all those ganglion cells are gathering, and they're going to leave the eye, okay, as the optic nerve. Which means if any light waves fall upon that region, there are no photoreceptors. We're not going to be able to see anything. And that's called the blind spot. And it's another thing, and I haven't done it in a while. I did it as a kid, actually, that if anyone's done this for blind spot, I can't do it here, but you basically put a small little X on a note card or something, and you hold it up, and basically you can see it, and then there's a point here at which it disappears. Okay, that's because those light waves are now hitting sort of the the optic disc here where it's leaving, and you don't see anything, and then you'll see it again. So there really literally is the blind spot that you can sort of demonstrate. Now we don't see a hole because again our brain processes and fills in the hole. It's not big, it's not like I don't see a head or something. It's like a little bitty X there that hits it, but it's it is the blind spot. Okay. So.
The optic disc.
Yes, the optic disc represents where the optic nerve is leaving the eye, and it's the blind spot because, again, there are no photoreceptors to change the information. So, last 4 slides of chapter 10, approximately. We go to the actual transduction, the changing of light into electrochemical. Let's do it. Who do we need? Rhodopsin. And so rhodopsin has 2 parts, and we're going to just show you what happens in darkness and in light. But rhodopsin basically has a protein that runs through the membrane all the way through, so it's called an integral membrane protein. And it's got a little helper there, retinol, which comes from vitamin A.
Opsin is the protein.
Opsin is the protein, retinol is this,
Vitamin.
vitamin A derivative, right? And it's attached. Don't worry about these words because we'll literally do it here. So, really, there are 3 slides, but here's the 2 slides, and you have it if you have your handout, which I recommend. All these words are next to A and B. We're going to show you what happens to this photoreceptor in darkness, what happens in light. And what I'm going to be saying, the steps, I'm literally saying exactly what's on the side. Okay? So to study this, right now you should be kind of listening to it, but to study it, it's literally trying to understand the steps that are sort of written here using the figures. Darkness, light. That's what these are. You take it right. It's another one of those things, it's opposite to what you might think. Okay, like that hearing thing was a little weird. And so let's follow this a couple times. We'll do it a couple times before we go on, because this is really it for chapter 10. There's no light here to start. Under those conditions, the rhodopsin is inactive. The retinal is still attached, and it's sort of just sitting there. There's no light to activate it. Now, rhodopsin works using a G protein. Okay, G proteins we talked about with the drug video, right? We had a couple of drugs that use G protein and our neurotransmitter. Dopamine used it. You need those drugs. You need to use those drugs, and THC used it. Now, those guys use a second messenger called cyclic AMP. And when cyclic AMP was up, that increased the activity.
That's the stuff that pumped, right?
That's being pumped out of that little G protein guy, yeah, like pumping it out. So the higher it is, the more activity of that neuron. This guy uses something similar. These use cyclic GMP, or little c GMP. So it's just a different messenger, okay? It's related too, but we don't care too much about it. But we do have to know cyclic GMP is that guy. And so the idea is that in the dark, and again, all of these are sort of here, we're just kind of reading it, the rhodopsin and its associated G protein are sitting there, okay? They're not doing anything, they're inactive. But the levels of the second messenger, cyclic GMP, are high. That means the cell is partially depolarized. These channels are open, resulting in neurotransmitter released onto the bipolar cells. Remember, the bipolar cells were next. Okay, it happens to the glutamate. So the idea is that you are, in the dark, you are releasing neurotransmitter onto the bipolar cells. In light, we're going to be somewhere different. So, but again, that's sort of the steps. Okay, and we'll go back to this if you want to. But in the dark, we have this idea that these guys are inactive, but the second messenger is high. It's sitting there high. You have this idea that if these are high, it's opening up channels, causing depolarization, resulting in neurotransmitter released onto the next neurons, which are the bipolar. What do you think is causing the neurotransmitter to exocytose? Calcium. Right? It's not shown here, but remember, like I said earlier, calcium is always causing the actual neurotransmitter release. That's the dark. Reading all this with the figure. This is what happens in light. So the words are here, we're trying to follow with the figure. Light's going to hit the rhodopsin, and guess what? Retinal is leaving now. And that's going to make this opsin protein active now. We're going to call this bleaching the pigment for a reason. So when retinal detaches, we're bleaching it. That's just the word they use. And we'll come back to that in the last slide. So light comes in, it's going to, by retinal leaving, opsin is now active. It's going to go through this. It's going to activate the G protein. So it's going to activate transducin. Now what transducin does, it's kind of similar to THC, right? It's going to decrease the second messenger. Okay, in this case, cyclic GMP, which is going to hyperpolarize the cell and decrease neurotransmitter release. So it's exactly the opposite of what you might think. In the dark, by the system, we're releasing neurotransmitter on the next neurons, the bipolar. In the light, we're actually decreasing it. So it's opposite to what you might think. But remember, we're a long way from the brain, and it could be that these things are what? Inhibitory, right? So if you're inhibitory signals in the dark and you're losing the inhibitory signal, it sort of makes sense how you might see in the end. But you kind of sort of realize, right now, this is what the level of transduction what we have to sort of realize. So one more time on it and see if there's any questions. In the dark, no light coming in. So we have basically the rhodopsin is inactive sitting there. The G protein is inactive. They're just sitting there. But second messenger levels are high. Cell is depolarized, releasing neurotransmitter to the next cells. In the light, retinal detaches. Now this guy is active. It activates the G protein transducin. That cuts up. You can almost think of scissors. It decreases cyclic GMP, and without that second messenger, the cell hyperpolarizes, less neurotransmitter release. That's dark and light. Any questions about that? Okay, you go from a bright light to dark. Are you able to see very well?
No.
So the last slide of chapter 10 is this. It's the idea that when you bleach the receptor, which is with the retinal leaving, as long as it's out there, this can't basically transduce another photon of light. You've got to reattach, okay, and basically unbleach. So you've got to reattach the retinal to happen. And so if you're going from a bright light, okay, you've bleached a lot of receptors, and you go to dark, it's going to take a given amount of time to basically recombine, the retinal and make it so you can actually, process again. That's why it's sort of hard at the beginning to actually see if you come from bright light. You bleached a lot of photoreceptors. Again, it's sort of right here. It takes time to reattach and adapt. The actually was a city student too. Again, I've taught this maybe 7 years now. So back in year 1 or 2, there's a lot of military. You might be in the military as well. These people that were talking came from Iraq, so it was back in Iraq, and they said when they were going to go out and look inside these buildings, they would have them basically have one eye shut, before they went in, one eye open, so that when they went into this dark place, that eye was not bleached at all, and so you were able to see much clearer right away instead of having all your photoreceptors bleached. Is that right?
No, I said so there won't be shock that both eyes are bleached.
Yeah. So the eye that's closed now will be completely ready to go and be able to detect low levels, of actually activity really easily, even though the other one will take a little time to adapt. So it sort of scared me. Okay, but I'm like, okay, but it did relate to this, so I decided to do the story. Believe me, it scared me a lot. I couldn't do that stuff. Okay, I'm a coward. I'm afraid to just go home to my wife late. Okay, that's what I am. It's like, oh my God, what's this going to be like? I have one eye closed, so I can't. Any questions? Oh, we got to do this, I'm sorry, and then we're done with chapter 10. And we will start on chapter 12, because again, the more we do today, it'll just be easy stuff, especially if you've had anatomy, but even not, then we'll be better off for Wednesday. Cell site, specialized cell or dendrite?
Specialized.
And this is why I'll talk in a minute, the book is a little off. And of course it is a photoreceptor. If you read the book, actually I have to see if this new edition does it. It used to call these, whether they're neural or non-neural, and they would do that, which makes it easier in a way. So they would call basically neural, non-neural, and they call these rods and cones non-neural And somebody came from me from other school, maybe UCSD, and said, photoreceptors are neural cells. And I'm like, yes, they are. And so it's really not a good way to do it. That's why I stopped doing it that way. So that's why, even though it's wordier, I'm describing things as either the dendrites themselves or specialized cells that will synapse upon dendrites, in this case, bipolar cells. So know it is sort of like this idea for that. Any questions on chapter 10 at all?
So I noticed that the neurotransmitters glutamate, isn't that the major?
It's usually the major excitatory, right? But it doesn't apply here a little bit. So, no. Just to complicate our lives. All right, so everyone go to chapter 12 for a second.
What?
A couple years ago, I was on the droids. I kind of got out of control. Now I'm much better. He looks happy. Obviously, I think this is Photoshop. What are you saying? I'm pretty sure I didn't do it, but or else that's our governor a few years ago. He won a lot of things. Our ex-governor, sorry. I don't think it's our current governor. Muscles. So you can see the questions we're gonna be asking really in this chapter, and you're gonna see this again in a second. All we are concentrating on, even though we're gonna show the different types of muscles, all we're gonna concentrate on are skeletal muscles and voluntary control. I'm gonna show you some slides. I'll come back to that. I'm gonna show you some slides of skeletal versus cardiac versus smooth. But in this unit, this test, I'm not going to be talking about the differences between them, because the next unit, starting next Wednesday, will be cardiovascular, in which we'll look specifically at cardiac muscle cells and smooth muscles that are lining veins and arterioles to cause vasoconstriction, vasodilation. And then we'll compare them all. So I'm going to put a slide up here, with comparing them. But really, again, all we're going to concentrate on are skeletal muscles. I put that up as a reminder that, as I said earlier, that every test I can use agonist or antagonist. So now I can use, a nicotine agonist or a heroin antagonist, anything that I'm using. And so you still have to sort of remember the term. So again, an agonist will be used. It will basically be doing the same thing. Like, that was a good example. Nicotine actually acted as an acetylcholine agonist, right? It basically acted just like the natural acetylcholine. It came in and stimulated the cell. The opposite is an antagonist. An antagonist will basically, decrease. Again, I don't like no response. It will decrease the response. Okay? This will do the same response and maybe even increase it. This will compete and therefore decrease it. Antagonist blocks, agonist does the same thing. So don't forget that, because I'll put those in on every test. So again, I put the slide for these, but again, I'm just, you can sort of be half brain dead or just sort of look at it, back of it, because it's not tested yet. But when you look at skeletal muscles, we are going to be talking about this. And we've talked about it in lab, and we will tonight as well. They're going to be controlled voluntary motion, somatic motor neurons. And they're striated. That's what we're going to talk about. Briefly, let's just look at cardiac and smooth muscle, see the difference. In this case, it's not controlled by somatic. It's going to be controlled by sympathetic and parasympathetic and some hormones. Some tissue can contract spontaneously, i.e. the SA node, etc., and the heart that we're going to talk about. Smooth muscle is very different. It's not striated at all. It's controlled like cardiac, sympathetic, parasympathetic, and hormones, and like cardiac, someone can contact spontaneously. These can be blood vessels, the GI tract, etc. But we're not memorizing this. No, or we're not looking at it. So here's what we're doing, or we're starting to do today. And that's the beauty of this unit. Chapter 10 just took us up to here. We're literally only going to cover this efferent pathway, the voluntary control using those motor neurons of our skeletal muscle. This efferent pathway, using smooth muscle, cardiac muscle, comes next unit. And then we'll have a complete picture. So this one's sort of nice, especially compared to the first time. Terminology just to get into your head, if you haven't been exposed to this, is we like these sarcos, okay, for muscle. So, but when we're talking about a muscle fiber, that's actually a cell. That's one cell. It's not really like a fibrous extracellular thing. That's what we call a muscle cell. And of that cell, the membrane's called the sarcolemma, the cytoplasm, the sarcoplasm, but this guy's going to be important. So the sarcoplasmic reticulum, it's obviously, comes from endoplasmic reticulum. It's going to be very specialized because it's going to basically hold a very important guy who is, what does sarcoplasmic reticulum have?
Yes.
Oh, we'll surprise you right now. Okay? Stay tuned. We'll write that question. What does sarcoplasmic reticulum have? And we're going to tell you. You just made a molecule very sad. Okay, but we'll look at this. Now, what we're going to do, this is again, is the overall. If you do anatomy, you're going through all this fascicles, connective tissue. But when you look at a muscle, we're going to be concentrating on what's happening in this one muscle cell, this one muscle fiber. But if you look at a muscle, again, you have fascicles, okay, which each contain bundles of muscle cells, and then we're going to look within it. So there's a lot of fascicles. So your muscle consists of a lot of these, but we're going to be looking at one cell and what's happening within that one cell. Of course, in parallel, it's happening to all the cells and all the fascicles in your muscle, so it actually at once. But we're only concentrating on this. It is interesting. Muscle cells do contain more than one nucleus, unlike any other cells. They're multinucleated. So that's what it's looking at. But we're looking at that. So a muscle fiber, again, is a muscle cell. We take sort of a cross-section of it. And again, right now we're just getting oriented, so don't freak out. But the idea is, if you look at it, again, it has a membrane around it, and we're calling it the sarcolemma. It has extensions that are going to be a better picture in a minute of the sarcolemma that go deep within sort of the cell, and they are called T-tubules. We'll see that. But within, again, if we just sort of make a bigger picture of a cross-section of one muscle fiber, so it's a cross-section, so this is one muscle cell. Again, we have these T-tubule extensions, but we have these guys, many of them. And what I'm talking about are the myofibrils. So within one muscle cell, we have dozens and dozens of these myofibrils. These are going to be the contractile units. These are contractile proteins, and we're going to look specifically at this. You can already see that they're sort of arranged in an overlap of these thick filaments and thin filaments. And every muscle cell has many of these running in parallel. When we signal, which we're going to talk about, we're going to see contraction of these units. That's going to contract the muscle. So we have all these myofibrils, again, that we're going to look at specifically, and wrapped around them is the specialized endoplasmic reticulum, sarcoplasmic reticulum, and guess what it contains? Calcium! Remember I said calcium was sad at the beginning? It's like, I'm the most important, ion out here, okay? I don't care about potassium. Sarcoplasmic reticulum contains calcium, and calcium is going to be important for causing a muscle to actually contract, whether it's this muscle or it's cardiac, all the way around. Because if you looked at our picture of a cell, okay, in general, again, sort of the circle of life, what ions do we have concentrated in the cell? Potassium, protein, overall negative, and outside. And calcium. So the cytoplasmic level of calciums are very low. Okay, extracellular very high, but especially in the skeletal muscle and all these muscles actually, we have calcium contained in the endoplasmic reticulum. Okay, in this case we're calling it sarcoplasmic reticulum. Calcium is like a psychomessenger, and we've already kind of seen that from neurotransmitter release. In this case, the idea is when we let this out, it's going to cause muscle contraction. Skeletal, smooth, cardiac, exactly. Okay, but right now it's contained in here, and so we're going to show you. We're going to signal the release of that. That's going to cause contraction, and then we're going to pump it back in. Okay, so the sarcoplasmic reticulum that's surrounding every myofibril is involved. It contains calcium. That's our signal molecule. So, if you look at a myofibril, what you see, and again, what I want us to know is sort of down here. We are not going to have to know what is the I band, what is the H zone, what is the A band, what is the M line, okay? You could do that in anatomy. Okay, I want us to sort of see what we're going to, the overall structure of this, and that the 7 steps of what's going to cause it to contract and relax. But what we do have to know is down on my list here. So a sarcomere is the basic unit of contraction. When we signal the muscle to contract and the myofibrils to contract, we're going to see that these thin filaments, shown here in red, are going to be pushed inward relative to the thick filaments in blue. And that's going to shorten the sarcomere. We have sarcomeres all along the myofibrils, and so they'll happen simultaneously and the muscle will shorten. Again, YouTube videos, I mean, actually I put a site on this for one, are the way to, instead of me doing this, because what does that mean? To actually visualize this happening. But to get the structure of it, you can see that you have this initial overlap. And what's going to happen again, first of all, you've got to know that the thick filament is made of myosin. Remember, these were cytoskeletal things we looked at. Actin is the thin filament. Actin and myosin. And if you look, we have an overlap. And this is what's going to give the striations. In fact, let me go to this picture here, because we have a real micrograph here. The idea is, when you look at the striation pattern that we see in skeletal muscle, it's because if you look at one area, you're just seeing the thin filaments. Here's an overlap of thick and thin. Here's just thick. And that's where some of these names are defining that I just don't care about that you define. But that's why it's striated, these different overlaps. But here's the overall. Okay? The overall is that, because it's kind of shown here, that when we're going to stimulate, we're going to go from this partial overlap. We're going to show you how these actin, okay, so these thin filaments are basically pushed inward relative to the thick filaments. These are sliding inward. There's more cross-linking, more overlap. And as it does that, each sarcomere shortens from here to here. Remember, these are all in parallel, all along muscle fiber. That's what's going to cause the muscle to contract. But the fundamental unit of contraction will be this base unit of the sarcomere. So, just to introduce the players, and then we'll stop, but I want to show you the steps so you can actually look at them. When you look at myosin, we're going to look at myosin and actin together. And then I'm going to show you the steps that we'll do next week. Actually, there's only like 10 or Wednesday, there's only like 10 or 15 minutes really of the chapter left after that. So, but if you look at it ahead of time, you'll see what we're going to do. But myosin and actin, if you actually look at the thick filament, the myosin, you actually see that it's sort of interesting here. It's got sort of, this tail here, but it's got this region here. It's got sort of, again, cartoon version, but a hinge region and a myosin head, which is going to attach to the actin. And you see a hinge, you're thinking, this is going to do something. And what it basically is going to do is we're going to use energy to push this out, bind to an actin molecule, have it go forward, move the actin in, release. Push it out, find the next one, and so we're going to ratchet that actin inward using this myosin head. Coming up on Wednesday. If you look at the thin filament, we're going to tell you that not only is it actin, we're going to talk about these guys, troponin, tropomyosin, and titin being important for us. The bottom line is, because I'm going to stop here, is, because I just want to start it next time, is when we look at muscle contraction relaxation, okay, and I'm going to have pictures of this. When we look at this, and we'll just do it next time, I've sort of summarized the whole thing in 7 steps, okay? And that's going to make this a lot easier. So we're going to, again, next time we'll go through sort of what's happening in those 7 steps, and actually, and if you want, by the way, besides, because I think you should look at it at least, let me get to it. If you want to see at least one sort of nice YouTube, which after we go through that actually does show it instead of me doing it. This is on your PowerPoint. You can actually go to that one. There's plenty of others too. This one didn't give, some of them give too much information, like that on that testing. This one actually kind of gave what I just described in those previous slides. So you can look at those, but literally next time all we have to do is this and talk about slow and fast twitch muscle. You'll see there's not much material. Again, half hour at the most. And then we should be going over, you should be looking at those extra questions, make sure that you sort of get those, and we can go over that, anything else you need to go for the rest of Wednesday.
Oh, we don't have lab Wednesday, right?
You don't have lab Wednesday at all. I'm gonna stay here for as long as people need to.
Can you go back to the YouTube?
Go back to which one? The what?
Is that on Blackboard? The YouTube?
Oh, yeah, it's all this, sorry. I'm not quite, well, this PowerPoint is, and you're loaded in Blackboard, so you can actually look at this, or you can write it down now, I don't really care. Okay, so, I'll see you guys in lab in a few minutes, people that have lab.
Thank you, Professor.